I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to bless this class, Lord. In your name I pray. Amen. All right, so as I've told you guys, I want you to watch a video on section 14.6, which is on Galois groups of polynomials. Essentially, what we show in that section is that if you take a sort of arbitrary polynomial and look at the Galois extension for that polynomial, you get the symmetric group on n symbols. Which in some sense is why the study of Galois groups really amounts to a study of subgroups of the permutation group. Because all Galois groups, in some sense or another, appear as subgroups of the permutation group. But I think what gets lost in that is that, we prove, what's that theorem in Algebra 1 that we prove this in Algebra 1, right? Is it Cayley's theorem? We proved
like
abstract algebra 1. There is only abstract algebra.
Sorry, I just didn't know what we were talking about. I was like, what, 7th grade? I was like, I don't remember proving Cayley's theorem in 7th grade.
All right, so that we look something like essentially left multiplication in the group corresponds to the correspondence between left multiplications in the group and reassignments of things in the group to other things in the group. So if you label the things in the group 1 through n, if it's a finite group, then essentially that says that the group can be realized as a subgroup of the permutations on n symbols, right? So any finite group can be realized as a particular subgroup of Sn, all right? And so there are a few different ways to look at that. I mean, one way to look at it is permutations are, sort of like matrices in a sense. They're some sort of blank canvas on which you can draw any finite group. They're an incredible, like saying something's a group of permutations really doesn't tell you anything. Not much. It's very, very general. What's permissible in Sn in general. So that's one viewpoint. But from the perspective of Galois theory, it's more than saying that the Galois group is a subgroup of permutations. There's more structure to it, right? Because it's the permutations that are doing something. They're mixing together roots of the polynomial that is in consideration. So there's actually more to the way Sn interacts with Galois theory than, say, just Cayley's theorem in abstract algebra 1. It's not that kind of identifications. It's much more structure. Anyway, just a thought. So section 14.7 is on solvable and radical extensions, of course leading to the insolvability of the quintic. And of course there we're talking about an arbitrary quintic. There are particular quintics which we can solve. All right, so let me share with you guys some definitions. First of all, what's our goal? Is the goal is to describe when can we find the roots of polynomial equations with using radicals, right? And so we want to make that a little bit more precise. So he says he first wants to define a simple radical extension. What's a simple radical extension? So you take f and adjoin what? Right, like the nth root of a, right? Where this denotes some 0 of x to the n minus a, right? As a polynomial in coefficients in the field. All right. He says the following. He says, since all the roots of the polynomial x to the n minus a differ by factors of the nth roots of unity, adjoining one such root will give a Galois extension if and only if the field contains the nth roots of unity. So let me write that out. Since all roots of x to the n minus a differ by product of nth roots of unity, adjoining one such root and, say nth root of a will be what? We'll give a Galois extension if and only if and only if what? Right, if and only if the field contains the nth roots of unity. Let me go back to our. Why is that? What does that make sense to you guys? The sentence that I've just said. I mean, so clearly that will be 1, 0 for it. So it splits off x minus nth root of a. But remember, it's a Galois extension. We have 4 characterizations. The one of which I like the most is that it's a splitting field. Right? A Galois extension is a splitting field. So if it is a splitting field for this, then that means it has to have all of the zeros, right? And so all of the other zeros are obtained from taking the nth root of a and multiplying by an nth root of unity. So, and the field, what field? I mean, I would say that the field we're talking about is f adjoin the nth root of a, right? We're not talking about the original field. Sometimes if you adjoin one root, you get the others, right? Sometimes you don't, Just some reminders. So let's see here. How about f of x equals to x cubed minus 2? This example has served us well. If we look at this as a polynomial over q, what's the deal? So we can look at the extension, right? Q adjoin what? Q adjoin the cube root of 2, right? Is not Galois over Q because it doesn't contain the roots of unity that we need. It doesn't contain the third roots of unity. That's what we need here. That's 1, 0 for that polynomial, but there are 2 others which happen to come in a conjugate pair. So, right? Now, in contrast, if we looked at this, same polynomial, right? But instead, look at it as being a polynomial built over Q adjoin I. Right? If we look at that as a polynomial with coefficients, possible rational linear combinations of 1 and I, then if we look at Q adjoin I, adjoin the cube root of 2, well, that will be Galois. That will be Galois over Q because I happen to know that you can build the, I think you can build the third root. Is that enough? Am I wrong? I may still be wrong. How do we get what is the third root of unity? I might be wrong, guys. What's the omega 3 or rho, whatever you want to call it, exponential, 2 pi I over 3. I think I might be selling you a bill of goods here. What is that? right? So it's minus 1 plus I root 3 over 2. I don't think I can build that square root of 3 unless I have, so I think this is still not, I don't believe this is actually a,
Can you switch it to like square root minus 3?
yeah, I think if we do that, if we look at it as q adjoin like I square root of 3, or like you said, square root of minus 3, sure. Then I think it's clear that you can, if you have a field which contains I times the square root of 3 and also the cube root of 2, you can build the third root of unity using I and the root of 3, and dividing by 2 and then subtracting a half from it, all those things possible in Q. And of course, the other third root of unity is just the square of that, or the complex conjugate. And so, yeah, this will be Galois over Q. All right.
Why is that one a square root and not the cube root like the other one? The one with the square root of 3.
Because the point is I need to, the way this factors, right, is x minus the third root of 2, right? X minus omega times the third root of 2. X minus omega squared times the third root of 2. So generically speaking, the solutions of x to the third equals to 2 are the cube root of 2, and then like omega times the cube root of 2, and omega squared times the cube root of 2. I don't need, it's because it's, all right. Okay, well, that's an example. Maybe a different example, something like x to the, x to the fourth minus 2. What does it take to get a Galois extension for this? Well, if we look at Q adjoin the fourth root of 2, how's that going to work for us? We can do this, right? I need to give this a name because I'm sick of writing it. Well, poor planning on my part mostly. Okay. So this is, put that there. So like that, right? And of course this we can factor into x minus fourth root of 2, x plus the fourth root of 2. But then over here, well, that I can't fix that with what this is irreducible over q adjoin the fourth root of 2. But what I know where it does split, right? I just need to use my imagination and say, okay, well, if I can introduce I on the scene, right? Minus I times the fourth root of 2. Plus I times the fourth root of 2. Then, so apparently the Galois extension that I need here to split x to the fourth minus 2 is what? If I adjoin I, right? So this is Galois. Over Q, yeah? Because it's the splitting field for x to the fourth minus 2. Do you guys agree? So I hopefully you see the importance of the roots of unity in this discussion. All right, so that's actually a little bit of a digression for today, honestly. So let me get straight to the definition that is the one that I'm most interested in. So that's a simple radical extension. the point is that it may or may not be what you want to get the Galois, to get the Galois extension for your polynomial, but it's close, right? You just have to throw in some roots of unity. I think I can erase here now. So next up, I'm going to give you the definition of come on. I thought that was called a, son of a gun. I thought that was called a radical extension, but I don't see him saying that. He says he's going to call it a root extension. Okay. All right. An element alpha which is algebraic over F all right, can be expressed by radicals or solved for in terms of radicals if alpha is an element of K which can be obtained by a succession of simple radical extensions. All right. So let me make a nesting here to try to put that up on the board. So we start with F. That's I think he calls it equal to K sub 0. That's a subset of K1. That's a subset of K2, and so forth and so on until you get to K sub S, he calls it, equal to K, where at each stage, the next extension is formed by adjoining an nth root of a sub I for some, let's see, I'll just write down, where ki plus 1 is equal to ki adjoin some nth root, and I think the n is not the same everywhere, it's n sub ith, my eyes, n sub ith root of a sub I, where a sub I is an element of K sub I. For I equal to 1, 2, ... I guess S minus 1 in my current lingo. So like, 0, it starts at 0, doesn't it? Because like the 0th one would be that K1 is equal to F adjoin the n first root of a sub 1, where a sub 1 is some particular element in the field, right? And here, he says that this just denotes some 0 of x to the n I minus ai. All right. He says such a field K will be called a root extension of F. All right. It's a root extension of f. So that's part one of the definition. Part two is that a polynomial f of x can be solved by radicals if all of its roots can be solved for in terms of radicals. F of x and f of x can be solved by radicals if all its roots are found in some root extension of f. All right. Then on page 627, he gives her like a rather, I mean, it's quite a doozy of an example of this idea. I think this example goes back to Gauss. I probably would be well advised not to try to write it on the board. But the see here. He describes, I'll just write out the, well, I better start, make poor planning on my part. Alpha equal to minus 1 plus the square root of 17 plus the square root of 2 times 17 minus the square root of 17, close parentheses, plus 2 times the square root, big square root, 17 plus 3 times the square root of 17 minus square root of 2 times 17 minus the square root of 17. No, I'm just working this out right now. Minus, it's obvious, come on guys, square root of 2. Why, you don't see it? 17, what's your problem? Aren't you guys the seniors? See here, 17. You're not? Not as, oh, yeah, I'm just copying it from the book, really. You know, this is an example of a number which is obtained in a root extension, a radical extension of the rational numbers. And he said that this was used to construct the regular 17-gon in the field K4. And I mean, he describes how this is an element of K4, which he builds from, he takes Q, and then he adjoins Q adjoin the square root of 17, and then he takes that and he takes that and he builds, he takes that and he extends that by 2 times 17 plus the square root of 17. This is K0, this is K1, this is K2. There's a 3 and a 4, wait, well, there's a 3 and a 4 in the book as well. Anyway, the point is that horrible number over there is a algebra, is what is it? It is expressed by radicals, right? The point of this example is just to give you a sense that expressing something by radicals can be a lot worse than you're used to. All right? All right. I think I've made my point. Now, Lemma 38 is the following. It says, if alpha is contained in a root extension, K, all right, then alpha is contained in a root extension which is Galois over F, and where each ki plus 1 over ki is cyclic. I guess at this point I owe you a definition of what that means, cyclic. What does it mean for an extension of one field over another to be cyclic, right? Do we ever define that? What do you think that means? What does this is cyclic mean? What did you say? No, it's not that. It's not that. It's not that kind. I mean, it's a good guess, but no. The definition at the start of the section says an extension K over F is said to be cyclic if it is Galois with cyclic Galois group. This means that Ki plus 1 is Galois over Ki with cyclic Galois group. All right. Have we seen any cyclic extensions in here? Remember the cyclotomic fields? We mentioned the cyclotomic fields have cyclic Galois group, right? So an example of this would be Galois groups are cyclic over the rationals. Excuse me, the cyclotomic fields are cyclic over the rationals, if I remember correctly. All right. By the way, it's not an accident that those, I mean, the Galois, the cyclotomic, the cyclotomic field has the zeros of what polynomial? Well, how do we define it? It was the splitting. What does it do? It splits what? I mean, doesn't it, am I wrong? Does it split this? Well, I feel like it's x to the n minus 1. It splits that, but that's not irreducible, right? I mean, this is, inside this has phi n of x as a factor, right? As an irreducible factor. If I recall correctly, phi n of x is built of x minus nth roots of unity, where those are the primitive nth roots of unity. So the order of phi n is little phi n, right? And then, if I recall correctly, q adjoined the nth root of unity is the so-called cyclotomic field, right? I'm really just reciting results that we saw back in section 14.3, right? I mean, really it goes back further, right? Where we actually introduced that was back to chapter 13 thing, wasn't it? 13.6, was it? Yeah, cyclotomic polynomials and extensions. And the Theorem 41 on page 554 says the cyclotomic polynomial phi n of x is irreducible monic polynomial in z adjoint polynomials with integer coefficients, and it has a degree little phi n. And then we also have corollary 42 that says that the degree over q of the cyclotomic field of nth roots of unity is Euler phi function of n. All right. So those things put together, I think, show you that q adjoined the nth root of unity is the splitting field for phi n of x, right? I'm not, this might be true, but this is definitely true. All right. So my point to you is that this is an example of a field, which is a splitting field for this polynomial, right? And what's the Galois group of a polynomial? Do you remember how that was defined? The Galois group of a polynomial is the Galois group of its splitting field, right? So this is, by definition, the Galois group of Q adjoin zeta root n, right? I mean, fine, fixing Q there, happy? But of course, that's unnecessary because all automorphisms of this field fix the prime subfield Q. But the larger point is, in the earlier section in chapter 14, we proved that this is cyclic, right? And if you look at that, there's something to be understood from that. All right? What is it? So I'm trying to find the... what I'm referencing is the discussion on page 585 to 586. That's where it's explained that it's got a cyclic Galois group, okay? But taking a step back, the solutions, right, if you look at phi n of x equals to 0, are the solutions to this all expressed by radicals? I mean, they are. That's the thing, is if we look at the particular polynomial x to the n minus a, that we can find solutions for by radicals, right? The trouble is when there's more than just x to the n, when there's more stuff. You know, there's x to the n minus 1, there's x to the n minus 2, there's lower order terms in the polynomial. Can you still solve for radicals in that case? So this much, we have already obtained data that if, here's an example of, anyway, a polynomial which we can solve by radicals, right? And the Galois group for this example is cyclic. That makes you think maybe expressing answers in terms of radicals has something to do with the Galois group being cyclic. That idea is too simplistic, though, because what we have to think about really is not just one extension, but a tower of extensions. All right? Okay, so that's lemma 38. Now, I cannot prove that. And the reason is it involves a section we skipped. So, but you can understand it. The statement of it you can understand. Theorem 39 says the following. The polynomial f of x can be solved by radicals if and only if its Galois group is a solvable group. All right? Now, admittedly, this would be hard for you guys to understand, as I have never defined solvable group, except perhaps in a homework exercise last semester, right? If that. I'm not sure I actually committed to that. I may have thought better. So let's see here. Let's think through the fundamental theorem of Galois theory, right? Suppose for a second, let's suppose for a second that the polynomial can be solved by radicals, all right? I want to suppose the polynomial can be solved by radicals. I want to think about basically applying Lemma 38 to assume that not only is it a radical extension, it's a Galois extension in the sense outlined in 38. Basically, 38 says that you can take your radical extension and you can soup it up and make it into a Galois extension. Whatever you were missing to split things as you go up the tower, you join them and make it split. You could be missing some things just adjoining square roots. But suppose this is a Galois extension, all right, by Lemma 38, and again, f of x can be solved by radicals. What does the fundamental theorem of Galois theory tell us about this tower of fields? What does it say? That there's a complementary what? Set of subgroups of the Galois group, is there not? How would that look? My question is, if G is equal to the Galois group of, let's see here, K over F, right? Then we also have this, trying to remember, I think I've chosen poorly. G Galois group of K over F down here. And let's see here. I have F down here. And then I have K1, K2. Eventually I get all the way up to K, right? Remember, what's the correspondent fundamental theorem of Galois theory says that there's the whole deal corresponds to what? Yeah, just the trivial group, right? And then what? There's, over this, there's a subgroup, let's say H1. There's a subgroup H2, right? And, I mean, H1 is, excuse me, how can I say this? It's that fixed field correspondence, right? So if you go back to the fundamental theorem of Galois theory, it says that there exists a sequence of subgroups, E contained in H1, contained in H2, contained in H3, contained in H, I can't count, HS, I suppose. Right? Yeah.
So the way that you have it listed now with the one right above G be HS, and then like HS.
Have I messed up my numbering?
No, I'm like just genuinely asking.
No, I'm genuinely asking as well. I think that should be HS minus 1
Okay.
and S minus 2. Thank you. I can't count. So this would be HS. If I number them that way, you know. I'm not sure about the numbering. I'm sorry. I'm trying to get to a point here.
I meant like the way that they're contained. Like the HS, the biggest one's at the bottom of the left-hand tower.
Right.
Okay.
Yeah. Remember the inclusion is, it's opposite for the fields versus the groups, and yet there's a bijective correspondence between the fixed fields and the fixed fields for subgroups and it's a page long, the theorem. I don't remember all of it. But the larger point here was the theorem also told us what? What was the relation between these subgroups? Like, what could you say about, say, H2 mod H1? More to the point, H1 actually is a normal subgroup of H2. H2 is a normal subgroup of H3, and so forth and so on. Hj is a normal subgroup of Hj plus 1 in my current nomenclature. That's another part of the fundamental theorem. That, yeah.
If H1 is a normal subgroup of H2, does that mean that it is also a normal subgroup of H3, or is that not true?
Yeah, I think so. I think, well, I mean, you get closure under conjugation by H2, but, you know, I mean, normality, that means that if it seems like there might be things in H3 which don't, is it conceivable that conjugation by things in H3 moves H1, whereas conjugation by things in H2 doesn't? I guess that's conceivable. I mean, I don't think normality of H1 with respect to H2 implies normality of H1 with respect to H3 necessarily. No. But, guess what? This equals to G. You know what the definition of solvable group is? A group is said to be solvable if there exists a sequence of subgroups like that, for which every, well, first of all, you have those normality conditions, and one more thing. You need that Hj plus 1 mod Hj is cyclic. This defines solvable group. Here, let me make sure I'm not glossing over something. Yeah? Make sure I haven't missed some kind of, you know. The definition for solvable groups is back on, oh, come on, page 105 possibly. 49's were there. Yeah, definition on page 105, a group G is solvable if there's a chain of subgroups, each one normal in the last, such that the, such that the quotient is abelian for I equals 0 to s minus 1. I was wrong. It's not. It was not cyclic. It was abelian. My bad. Sorry about that. I'm sorry. I don't know what I was thinking. Abelian. Now, all right, so I don't know if we have the abelian condition from this. I mean, we can at least form the quotients that we need, right? So a polynomial f of x can be solved by radicals if and only if its Galois group is a solvable group. How would I know? Can you guys, so solved by radicals, does that give me that, oh, why is it abelian? So if I'm applying lemma 38 to this arbitrary thing, right? Lemma 38, soup it up, make a Galois, apply fundamental theorem of Galois theory, I get a sequence of groups, right? But I get something else. Remember that each, right here, right? each ki plus k1 is cyclic. What does that mean? That means it's ki plus 1 is Galois over k1. Cyclic Galois group. Right? Does cyclic imply abelian? Is a cyclic group abelian? It is. So, I mean, we get cyclic from what's above, but then if it's cyclic, that implies it's abelian, which means that it is a solvable group. So that's the forward implication of Theorem 39. If we have solvable radicals, it implies that the Galois group is solvable.
So what you're saying, since it's cyclic, that's why it's abelian.
Right, and hence the group is a solvable group. The Galois group is a solvable group. And you can prove the other direction as well. All right? And this is the, this is the exclamation point, if you will, for this part of the course. This is where it's at. I mean, this is the whole goal of what we're doing, is to understand this theorem. Because, what does that mean? That means if you can find a polynomial whose Galois group is not solvable, what's that mean? Yeah, if there exists f of x with the Galois group of f of x insolvable, then f of x equals to 0 can't be solved by radicals. In other words, there does not exist a natural generalization of the quadratic formula for such a polynomial. And if there's one polynomial that fails at that order, then there's no general formula at that order. Even though we already know that the, x to the n minus a problem has solutions by radicals at any order, right? So what I'll do next time something hilarious happens, but the time after that, I'll actually go through the details of a particular quintic polynomial which takes S5 as its Galois group, the symmetric group on 5 things. S5 can be proved to be simple. Proving that a group is simple means that it basically doesn't allow interesting quotients. And if a group is simple, that implies it's not solvable. So giving that example next time will prove that indeed there does not exist a general fifth order formula for finding the roots of a polynomial equation. And I'll try to also dig into like the cubic formula and the quartic formula and try to look at some of those things because, that's part of what we're doing here. Hopefully I have time for it. I don't know. I've forgotten where we are semester-wise, but I know I'm past 3. But hey, we started 10 minutes late.
I know. I have to meet with.
It was for a good cause, though. I understand. I mean, it was for a noble cause.
It is good.
The most noble of causes, really. Math club was causing you problems, huh?
Companies.
Oh. Well, anyway, thanks, guys.